Thanks, Graham. Okay, so final stand density, as many of you know, is a pretty important determinant of crop volume and value. And over the last decade or two, we've done a lot of work at Scion to empirically model within Forecaster the effect of final crop density at the final fin on the crop value. And this work has been undertaken at the stand level, which does have some limitations, but is very useful. It's been an industry standard for a long time. But we thought the sort of genesis of this work was we thought that it would be useful to develop large-scale spatial surfaces of optimal stand density for forest managers. And I should mention that Mark Kimberley and myself undertook this work. Mark did a lot of the modelling that you will see, and I was involved in a lot of the writing of the papers that came out of this work, which was started around 2014. So it's been quite a long-term project. So the idea behind the development of this model was that we'd develop a simple model, and I guess we took that to a pretty extreme level. We developed it in Excel. It was good to see that Mark could work with Excel. And we only had a few very small number of model requirements that included rotation age, site index, 300 index, the net value of structural and prune grades, and the cost of pruning. And so this model was developed with these four inputs, and Russell has told me that it's freely available to any payers of a levy, so if anyone wants a copy of this model, just get in touch with me after the presentation. The useful thing about this model was that because it runs off site index and 300 index, we have these surfaces for radiata pine, site index and 300 index, so we can generate spatial predictions of the optimal final crop stocking. So when we did this, we were quite surprised to see that the model predicts a mean stocking of 676 stems per hectare across New Zealand, and you can see from here for the structural grade regimes that predicted values are very, very high, virtually everywhere, between 700 and 800. In most places, it does vary a little bit in the central North Island, but overall values seem to be largely above 500 and lower than 800. So the key point here was that at the time this is very much higher than the current stocking. After I talked to a number of forest growers about this, it seemed to be quite a bit higher than the actual stocking that was being run. So this clearly indicates that there is room for creating value by moving towards the optimal crop stocking. As you would expect, the optimal crop stocking for final crop stocking for prune regimes is quite a bit lower, and it does vary quite a lot, and that's as you'd expect because you're looking for a bigger SED for a prune regime than you are for a structural grade regime. So one of the useful attributes of this modelling approach, of course, is that you can look at changes through time, which is pretty much what we've done here. So you can actually output the net value within the Excel spreadsheet, and when you line it up for GIS, you can output the net value of structural and prune grade regimes for New Zealand. And then if you just divide the pruned regime net value over the structural grade net value, you arrive at the relative value if you multiply it through by 100, as we've done here. So if we look at a particular spot here, like for instance Taranaki, between 1995 and 1999, that's using the log values from that particular point in time, you get the prune regimes are around about 20 to 30% higher net value than the structural grade regimes. And conversely, if we look at this spot next to Lake Taupo, using log prices from 2015 to 2017, you can see that the relative value of the structural grade regimes was around about 20 to 30% higher than that of pruned regimes. This gives, these panels just parameterising the model using log prices from different periods going through time, and this is the average from 1995 to 2017. So the key thing I want you to take away from this graphic is the change and the profitability of prune versus structural grade regimes through time, you can really see that in the 90s, it was far more economic, far more profitable to grow a prune regime in New Zealand, and it really reached a sort of the best time for prune regimes was clearly 2000 to 2004. Then as the pruned log price came down, you got this transition point, 2005 to 2009. And then we have this change over here, 2010, 2014, diametrically opposed to 2000 and to 2004, when it was really the structural grade regimes that were better. And we have some easing of that situation with I think, an increase in prune log prices around 2015 to 2017, and you're getting some areas coming back into being more profitable for prune regimes. So once we'd done all this work, we thought, oh, that's kind of useful to know, and we thought we'd look for lines of supporting evidence, and John has presented some supporting evidence that was done subsequent to developing the model. But also, we thought we'd also try to run this all through Stampak as well, and actually generate a range of combinations of net value from Stampak using all potential combinations of 300 index and site index found throughout New Zealand plantations. So we ran that through using all the planting costs, the thinning costs, the pruning costs, the harvest costs, extraction, the whole lot, and we arrived at net value from Stampak. And what you're looking at here is a composite of this net value, just basically averaged it according to the weighted area within different productivity classes. So it's a composite value. And down here, the scale here indicates deviations from the optimal stand density. So when we look at this average, the zero would actually be 670 stems per hectare for the structural grade regimes. This is all for structural grade. And then the negative 200 will be 470. The positive 200 would be 870. So if we just look at this first graph here, you can see that there is a very strong increase up to the optimum that we predict from our Excel model, and then it flattens out a little bit after that. In terms of internal rate of return, you get a similar sort of trajectory. Most of the work's done up to the optimal, then it's a gentler slope after that, and similarly for the net present value. So what does this actually mean to the average grower? I guess what we're sort of saying from this work is that if you shift your final crop stocking 100 stems per hectare, which is quite conservative because we actually worked out it was a bit more than that when we reran the model and got a slightly higher optimal stocking, then you'll be getting $2,300 a hectare more net value out of the stand. Internal rate of return will go up almost 0.5%, and net present value will increase by $294 a hectare. So we scaled this up to see what the outcome was for New Zealand Inc., and this is all published work, so it's been peer reviewed. So basically, at the time, we just assumed from 27 onwards that every grower would thin their stand to the optimal final crop density for the structural regimes, just talking about structural here, not pruned. And that would happen for the next 28 years. So that's basically what you're looking at here, is the additional income stream over the next 28 years. We could have gone further. Obviously, it would have created a bigger net value, but when you discount it back, when you're discounting back from a long way out, it doesn't actually affect values much, so we just thought we'd stop there. And so if that operation was modified, then we'd be looking at another $1.7 billion for the industry in net value, which when discounted back to current time is $156 million. And the gross value is obviously a lot more than that. So I think that's a pretty good demonstration of what you can do through something fairly straightforward sort of operation.